Okay, now that we've talked about atomic theory and some of the development of subatomic particles and our understanding of those, you might wonder, so what is it exactly that makes one element different from another element? Why is gold different from copper? Why is platinum different from silver? And at a fundamental level, it has to do with the number of protons that are present. We have a way of looking at this where we can describe a few parts of an element. We can first describe its symbol, but then we also have these two terms, the atomic number and the mass number for an element. And I'll walk through those briefly. The atomic number is the number of protons or the number of electrons, since in the neutral atom, those should be the same. However, we primarily only talk about this as being the number of protons because in ions, as we'll talk about later, the number of electrons does not always equal the number of protons. However, for any given element, the number of protons is always the same for that element. That's why we often refer to the atomic number as being the number of protons. And this is fundamentally what makes the different elements unique, is the number of protons in the nucleus. If you have 6 protons, as shown here for carbon, then you have the element carbon. If you had 7 protons, you would not have the element carbon, you would have the element nitrogen. Now, there's also a mass number given here. And this is in superscript before the elemental symbol. This mass number is the number of protons plus the number of neutrons. And this is where we have a difference between Dalton's original postulates and what science has later discovered. So Dalton's second postulate that states that all atoms within a given element are identical to each other is actually proven to be incorrect. And that is a result of the fact that we have neutrons as a neutral subatomic particle. And the number of neutrons that we have can vary without disrupting the electrical charge neutrality of the atom, because neutrons are not charged. And this results in something that's known as isotopes, when multiple atoms within a single element differ from each other. And they differ because they have the same number of protons, that's what makes them that element, but they have different number of neutrons. That's illustrated here with this example of carbon. So we have carbon 11, carbon 12, carbon 13, and carbon 14. All of them have the exact same number of protons, and thus they are the element carbon. They have the same number of electrons because it's just neutral carbon atoms, but they vary in the number of neutrons that they have present. As a result, they do not, these 4 different carbon atoms are not identical to each other, and they do not have identical properties in terms of their nuclear properties. Some of these are radioactive, which you can learn more about in chapter 20 in your textbook. Now, in addition to the number of neutrons, the isotopes, and atomic number, when we look at the periodic table, we'll see a few different numbers show up. There's the atomic number, that's the number of protons, and that's what defines an atom as being that particular element. There's the atomic symbol, in this case K is for potassium. And then we have the atomic weight listed down here. Now, what exactly is the atomic weight? Well, the atomic weight is the sum of the weights of all of the different isotopes of a particular element times the, taking into account the relative abundance of each isotope. So what does that look like on a practical level? Let's just take this example here using carbon. So all of naturally occurring carbon is composed of just 2 isotopes, carbon 12 and carbon 13. Now, in atomic mass units, we're given the mass of each of these atoms or isotopes. So carbon 12 is just 12 atomic mass units, whereas carbon 13, it has another neutron, so its mass is 13.00335 atomic mass units. We're also given the relative abundance of each of these. So the vast majority of all carbon in nature exists as carbon-12, but there's about 1% that exists as carbon-13. So then what is the atomic weight of carbon? Well, we take the mass of the isotope times its relative abundance in decimal form, and we add that to the mass of the other isotope times its relative abundance, so that we have the relative contribution of each of those, and we come out and we simply sum those values and come out with the atomic weight for that element. That is how the atomic weights on the periodic table are determined. Let's get a little bit more practical. Let's go through a couple more examples of this. So the first is naturally occurring chlorine. It's also composed, like carbon, of only two isotopes. There's chlorine-35 and chlorine-37. And the relative atomic masses of each of those isotopes are given, as well as their relative abundances. So most of chlorine exists as chlorine-35, but there is about a quarter of all the chlorine that exists as chlorine-37. So then what's the atomic weight of chlorine? Well, again, we follow our formula. We take the atomic mass, the isotopic mass times the isotopic abundance in decimal form, and add each of those together. So we take the first for chlorine-35 times its relative abundance, plus the mass of the chlorine-37 isotope times its relative abundance, sum those, and then we get to the overall atomic weight for that element. This can also be a little bit more complicated. Boron also has only two stable isotopes, boron-10 and boron-11. And if we look up on the periodic table, we can get the atomic weight for that element. We can also look up the individual masses of the boron-10 and boron-11 elements. But then from here, what we're asked to do is to calculate, okay, given the final value and given the mass of each isotope, what is the actual relative abundance of each of those isotopes? This requires a little bit more algebra, but we can set it up in the following way. First, we know that following our formula, that the mass of boron-11 times its relative abundance, shown here as X, plus the mass of boron-10 times its relative abundance, shown here as Y, must equal the 10.81 value. And so we can plug in the masses, and we'll come out with this equation where 10.81 is equal to 11.0093 times X plus 10.0129 times Y. Now we also know that the total abundance has to be 100%. So X plus Y in their percentage forms must be 100%. In their decimal forms, X plus Y has to equal 1. That has to be, that's essentially just the law that the sum of the parts must equal the whole. We must have unity. And so knowing that, we can simply rearrange solve for X in decimal form, substitute that into the first equation for X, and now we just have one variable, Y. We kind of distribute through, we multiply this equation through, we rearrange to solve for Y, and we end up with Y equaling 0.200. Now in decimal form, so 0.2 now in percentage is 20%. And because the sum of X and Y in their decimal form must equal 1, that means that X must equal 0.8. And so my final values here are that boron-11 has an isotopic abundance of 80%, whereas boron-10 has an isotopic abundance of 20%.